All right, so this is another form of this. So this is row echelon form. So it's still going to use that Gaussian elimination. It's just our final form is a little different. So previously, this was the kind of forms that we were getting. And that's what we were happy with. This is not what row echelon form is going to be, a row reduced echelon, reduced row echelon form. So if a row does not consist entirely of zeros, then the first non-zero element in the row is a 1. So that means that we need to make sure that our leading row has a 1. So this is called your leading 1. For any two successive non-zero rows, so like this here, the leading 1 in the lower row is farther to the right than the leading 1 in the higher row. So we're still getting this here. We should have a leading 1 and then everything following it is zeros. Then we should make sure our next one is here, is what that's telling us. Then all rows consisting entirely of zeros are at the bottom of the matrix. So if the fourth property is also satisfied, a matrix is said to be in row reduced echelon form. Each row that contains a leading 1 has zeros everywhere. So what we're saying is it should look like this now. We're going to call this not XY. Sorry, I was going to use AB. So this is our old version where this didn't have to be 0. I know this has sounded really wordy, but all this was is saying that we're getting this, what is called reduced row echelon form. So what do we like about this form is that this is telling me is that X would have to be A, and Y would have to be B. So where the previous Gaussian elimination method was giving us two equations, one of them, it did tell me like what Y is. I could substitute back in for X and find X. This version, we don't have to do that anymore. It's going to give us an A, or it's going to give us an X, and it's going to give us a Y. So it's giving us our A and B. So the way that we get to this is pretty much going to be the same way. It's just a little more work. So we want to know which of these following matrices is what we call row reduced row echelon form. This one is not, because these are not 0. This one is not, because that's not a 0. This one's not, because we don't go 0. We don't go 1, 1, and 1 is what we should look like. This is the correct one. Everything should be zeros, and then we have all our ones going down like this. Because we would be able to look at it and go, okay, X equals this, Y equals this, and in this case, Z equals this. Here, I can't tell that with each one of these. So these two would satisfy row echelon criteria. This is the one that satisfies the reduced row echelon form. Like I said, in B, we have a non-zero element in our first row, and C consists entirely of zeros in one row, which is also a problem. So these two are our winners. This one is just the reduced. All right, and this is what we're heading for next, because this we've already done. We want to do reduced row echelon. So once again, this is the Gaussian-Jordan Jordan elimination method. We perform row equivalent operations on a matrix to obtain a row matrix in a row echelon form. We continue to apply these operations until now we are in reduced row echelon form. So we already did this one, so we're going to use this as our first example. So we're going to kind of go back over some things that we did last time. Trying to grab my right tool here. So there we go. So this one we know was 1, 2, -1, then -1, 1, 3. So first thing we did is we added row 1 to row 2, and that was how we got our new row 2. That's right. The top row stayed the same because that was not the one we were changing, it's just the bottom. So if I added these, I get 0. If I add the 2 and the 1, we got a 3. If I added the -1 and the 3, I got a 2 here. Then from there, what we had done last time was then, I don't think I need that long of an arrow, is I just took row 2 and I divided everything by a third, so then my first entry is a 1. And that was going to be my new row 2. So 1, 2, -1, 0, 1, 2/3. All right, so this is where we had stopped last time. And this is where we had, things are overlapping here a little bit. This is where we had, like I said, this was row echelon form. So what we're wanting to do is to continue this until we have something that looks like this instead. So we're trying to get all the way down to that reduced row echelon form. So what we'd have to do here is now I have to figure out how to get rid of, sorry, my tools confusing themselves. I need to have to figure out how to turn that into a 0 because that's what we have here. So what we can do is this, is that I can take row 1 and then I can add row 2, but if I double everything by, or not double it, but multiply everything by a -2, well, then I have a -2 here, a +2 here, and I can eliminate that 0. And that is going to be my new row 1. Okay, so what we have here is that we're just keeping row 1 the same. Row 2, we're multiplying everything by a -2. And when I do that, when I add this up, I'm going to end up with 1 here, 0 here, -1 minus a 4/3. That would be -7/3. That's what my first row is going to be now. And we see that we got that solution that we had before. This is telling me that x is going to be equal to -7/3. And this is telling me that y will be equal to 2/3. So this is all we're doing when we're doing Gaussian-Jordan elimination, is that we're just extending this until we're in what we called our reduced row echelon form. And once we're in that form, then we already know our variables x and y, or if we have a 3, then we know x, y, and z. So take a minute and see if you can try to use Gaussian-Jordan elimination on 6 and 7. If you can just get to row echelon and solve it, that's still okay. I just want to see if you can get all the way down to reduced row echelon form. Okay, so for number 6, this would be sorry, this would be your augmented matrix. So like I said, we're looking at something that looks like this. So we want to make sure that these are ones, these are zeros. So first thing I'm going to do is like, I'm going to turn this number in here into a 0. Change my color here for a second. This one I want to be a 0. So what I can do is if I add those equations together, that one, that negative one are going to cancel each other out. So I'm going to take row 1, add it to row 2, and I'm going to use that to replace row 2. So I'm going to make myself a new row 2. So if I add these, well, the only one we're replacing is the bottom row, so the top row stays the same. 1 plus minus 1 will be 0. -7 plus 5 will be -5. -3 plus 18 would be 15. So we've accomplished this part so far, and we got this part. So the next thing we'd probably want to do is tackle this because we want this to be a 1. So what we can do is I can take row 2 and I'm essentially going to divide it by, well, not just 5, because I want there to be a positive 1 there, by -5. And that's going to be my new row 2. So once again, the top hasn't really changed, it's just the bottom. So if I divide this by -5, I have 1. 15 divided by -5 is -3. So the next thing I want to do, as I've accomplished this, is I want to turn this into 0. Once I'm there, we're in the form that we need to be. So to do that, what I'm going to do is I'm going to do another row addition again, except I'm going to take row 1, and then I'm going to add, because what I need here is that this 0 or this 1 to be a 7, so I can make a 0, is that I'm going to take row 2 and I'm going to multiply it by 7. And that's going to be my new row 1. So if I do that, let's put it over here, my new system here, we would end up with 1, -7, a few things here, -3, and then I'm multiplying the row 2 by 7, so we'd have 0, 7, -21. So if I add those together, like I said, this is making a new row 1 for me, so row 2, that one doesn't change this time. 1 plus 0 is 1. -7 plus 7 is 0. -3 plus -21 is -24. So I have my solutions now. This tells me that x is equal to -24, and this is telling me that y is equal to -3. So my solution is -24 and -3. You can check it. I already did. That is the solution. Okay. So there's a little trick to solving this one. Might have been not very obvious right away. So there's no rule saying that I have to eliminate something in the first column to begin with. I can do the second column first. And don't worry, if you're feeling overwhelmed about this, we're going to give you a much easier method here soon. We're just required to show you how to do how to solve a system with a matrix. This is why we did this. So this is my augmented matrix. So one of the first things I could do, it's kind of like when you were doing elimination method, you looked for something that was a multiple you could eliminate. So we got 2 and a -8. So if I just multiplied this by 4 and then added it, I can eliminate this. So what I'm going to do is row 1 plus 4 times row 2, and I'm going to use that to replace row 1. All I'm doing is I'm going to try to make this a 0. That's one of the nice things about the Gaussian-Jordan elimination is that I just need to get zeros there and I can do it whatever order I want. I don't have to worry about leaving this space to be any other number. So if I did that, we would have 7, -8, and 12, but the second row would now be -16, 8, and 12. So if we add those together, what you're going to get in that new first row is you'd end up with a -9, then the 8s cancel, you get a 0, and your 12s cancel and you'd get a 0 as well. So what we have here is essentially is -9x equals 0. And I just need a 1 here. So what I can do is, it needs to be a positive 1. I'll just take a 9th or divide by a 9, that row 1, and then make that my new row 1 again. So I'm just replacing it. So now it can be 1, 0, 0, and then we have -4, 3. Oh, sorry, 2, 3. Okay. I'm going to erase this for right now so I can use this space, because now I need to make this 2 into a 0. So we're going to do that first before dealing with this, or sorry, wrong one. We need to make this 4 into a 0, which we're going to tackle before we try to make a 1 in this spot. It's pointing at the wrong number there. So the way I can do that is I'll just take 4 times row 1, and then if I add that to row 2, that's going to be a positive 4, -4, that will cancel out, and that's going to be my new row 2. So row 1 stays the same. Row 2 is now going to be, like I said, that's going to be a positive 4 plus this. It's going to leave a 0. 0 times 4 would be 0, so 0 plus 2 is 2. Same thing here, 0 plus 3 is 3. Now I just have to take 1/2 of row 2. That will be my new row 2. And you're going to end up with 0, 1, and 3/2. So as I've been saying before, this top, it's telling me x is now going to be 0, and that y is going to be 3/2. So my solution is 0 and 3/2, which I also checked that is the solution. All right, so for number 7, so one of the nice things about the Gaussian-Jordan elimination, where we're trying to get something to look like this, is that we want a 0 here. So I am not like bound by rules that keeps another number in that spot. One of the first things I can do is make that spot a 0, which is what I'm going to do. So this goes back to what we were doing elimination method. We were talking about looking for something that was a multiple that I can, because that would be something that's easy to eliminate. So like we have right here. I have a -8 would be on my y and a 2 would be on my y. So if I just doubled everything in the second row, I would end up with a +8 to counter that -8. So what I'm going to do is I'm going to try to turn this spot into a 0 first. There's no rule saying that I can't do that. I can do whatever I need to as long as those operations are correct to get in this form. So I'm going to write down what I was doing. So I am going to take row 1 And then I'm going to add 4 times row 2 to it, and that is going to be my new row 1. So usually I've been replacing row 2 first. This time I'm going to do row 1. So if I go through this, we're going to do it up here. The top row stays the same because I didn't do anything to it. It's the bottom one that changes. I'm multiplying everything by 4. So that row is going to be negative 16, 8, and 12. So if I add those together, so remember row 2, I wasn't doing anything to. That one's staying the same for right now. Row 1's changing, but 7 plus negative 16 would be negative 9. 8 plus 8 is 0. And negative 8 plus 8 is 0. Negative 12 plus 12 is also 0. So don't let that 0 fool you or anything. We don't care if this is a 0. We just need to be a number. We do care if this first entry is a 1, though. So I'm going to take a negative 1/9 or divide by negative 9, that row 1. That's going to become my new row 1, just so then my first entry is a 1, like I need. So it's going to be 1, 0, 0. This is still the correct form. Like I said, we never said these could not be zeros. So from here, I needed, go back to blue here, I need this to also be a 0. So what I can do is I could just take row 1 and multiply it by 4 and add it to row 2 to replace row 2. Because if I do that, we're going to have, now this would be 4 plus negative 4. So that would be 0. Put my first row up here. And then we'd have 4 times 0, that stays 0, times 2 would be 2. Once again, that's going to stay 0, times 3 will be 3. Then all I need to do is just make this a 1. So if I just multiply everything by a half in the second row, forgot to write, these are my new row 1, new row 2, and this is going to be new row 2. We would end up with 0, 1, and 3 halves. So this means my solution is x would be 0 and y would be 3 halves. I did check this out, so this definitely is a solution to this. So your solution is 0 and 3 halves.